In this video, we're going to look at series and parallel circuits for GCSE electricity. So the first thing is obviously to make it clear what we mean by series and parallel, something that I think as teachers we find extremely easy, but students actually often get a little bit confused about. So a series circuit, more than one component in the same loop, and there's only one path for electricity to flow. In a parallel circuit, there are multiple paths for the current to flow. So this can be really easy, but I'll show you why students sometimes get a little bit confused. So here is a parallel circuit. Now there is more than one path for electricity to flow, here and here. There's also more than one path for electricity to flow here and here. So we might say that these two are in parallel with this branch. We might also say these two resistors are in parallel with each other. Importantly, what can happen is you can actually have these two bulbs are in series with each other, but they are in parallel with the other branch, right, with this branch here. So that distinction there, that you can have both series and parallels in the same circuit, is I think what sometimes gets students. So it sounds a bit basic, but I say this to my year 12s and 13s, and it does actually help, right? Imagine you're an electron going on your day out, right? Where are you going to go? Well, you can either go here or here, so these two things are in parallel, right? You have to go through this one, so this is in series with both of these, but then here you've got a choice. You can go this way or this way, so these two are in parallel. When you get to this way, you've only got one branch, so these two are obviously in series. When you get back here, you're joining back up, so all of this is in parallel. Right? That's quite a good piece of language and good exercise for students to do if they're struggling. So what do we need to know? We need to know that the potential difference or the voltage is shared amongst parallel components. So for example, if this was 12 volts, okay, and these are equal, then I'm going to have 4 volts across this one, 4 volts across this one, and 4 volts across this one. If the resistance is higher, then it gets a higher share of the volts. So an example would be, let's say 6 volts, and let's say this is 4 ohms, and let's say this is 2 ohms. The resistance here is greater, so it's going to get a greater share of the volts. And it's just a simple ratio. Whatever the ratio of resistances is how the volts are split. But it's a really important concept, this. Students often get it the wrong way around. Why is a big question. How do the electrons know to give more of their resistance here than more of their resistance here? So again, think back to this rope model. It works really, really well for explaining this question. Okay, you've got the teacher here that's pushing the rope round. This student over here grips really, really tightly, right? But immediately, as soon as this person grips the rope slows down everywhere and the current decreases everywhere because the whole rope is connected, right? And there is this kind of physical push from one atom to the next, right? And it's similar to the electrons. There's this push from the other electrons on it, right? So this explains this question really, really well, right? Without really having to say much more. What else? The current is the same everywhere. And one common misconception is that current gets used up after a component. So very often students will say this current is going to be less than this one. Well, it can't be. All the electrons have to go through the same way, so they have to have the same number of electrons here as you would have here. A really good analogy here is also the rope model. But another really good useful is if we start to have an analogy with height and GPE. So what we can say is imagine a marble run. At the top of the marble run, we've got a marble, okay? And then every time we go across a resistor, that is equivalent to a change or a loss of height. So the energy that it takes to go across the resistor is the same as this change in height and the same as the GPE lost. And then when we've got a wire, we don't really lose any energy, so there's no change in height. The second resistor, the second change in height, the second GPE. And this again is also a really good analogy, because the larger the resistance, the larger the change in height. And it also explains why when electrons get back to the start, they have 0 volts and then they end up with 6 volts. And it doesn't matter what has happened in the circuit, they always end up with 0 volts. They always use all of their energy because they always start at the maximum height and then they always end up back at the 0 height, so they can go back around the marble one again. So this can also lead us to the idea that resistance adds. If we want the total resistance in series, it's the sum of the first resistor plus the sum of the second resistor plus the sum of however many resistors you have. If we want to measure current, we measure it in series. So there's two consequences of this. Firstly, the ammeters have a low or 0 resistance because we don't want to affect the current, right? We purely want to count the particles. We don't want to affect it. So you could talk about an analogy about, if I was doing the register, but every time I call a student's name, I kick them out of the classroom, well, it's not a very good register because I'm affecting the number. I want to count without changing. In parallel, what do we have? Well, we have the current is going to be splitting across parallel branches. So here is probably where the rope model is not as good, and it's better to talk about one of the donation models that I talked about. So here we've got a parallel branch, and we've actually got electrons moving around, and they have a choice of going one way. So some of them are going to go this way, some of them are going to go this way. At GCSE, we don't really need to go into too much more detail, but if we wanted to work out the actual currents going through it, again, we're going to be looking at the ratio of the resistances, but this way there's one extra subtlety. So if that was 6 volts and I said that was 4 ohms and that was 2 ohms, well, the higher the resistance, the lower the current now, because the resistance stops the current going through. So this would only get 2 volts across it, and this would get 4 volts. So it's still a ratio, but it's going to be flipped. If sometimes this catches people out as well. If I had a circuit like this, and then I put a wire here, what's going to happen? Okay, the wire has 0 resistance, so it's a short circuit, and both bulbs will go out. So all of the electrons will take the easiest path. They'll go through the route of least resistance, and there therefore won't be enough current to make the bulbs light. And this often is asked at GCSE. What else is there to talk about? Well, the potential difference is the same across each branch. So it doesn't matter which way the electrons go, they are still going to carry the same amount of energy, the same amount of volts. And again, you can talk about one of these donation models, like the sweet shop model. The parent is giving money, and it doesn't matter which way the child goes, they have the same amount of money on each path. But we can also use this. This is still a nice analogy. We can now say that we've got a marble run. One way there's a loop-the-loop, the other way there's 2 resistors. And it doesn't matter which way the marbles go, they still have to end up at 0 height to end up back at the start again. So they've still lost the same GPE or the same energy each route, but we only have half the marbles going each way, or some fraction of the marbles going each way. The resistance in parallel is always less than the smallest resistor. And this is basically enough for the current AQA GCSE. So if you have a circuit and we have, 3 ohms and 10 ohms, then the total resistance will always be less than the smallest one, which is 3 ohms, right? Because there is simply more space for the electrons to travel, and so there's going to be fewer collisions when they go through each route. And I talked about this in a previous video. Imagine having 1 door for your whole class to get out compared to 2 doors. Well, it's obvious that there's going to be a lot less congestion when they can go through both doors compared to 1 door. If you want to know the full formula for working this out in parallel, then the total resistance is given by this formula. 1 over the total resistance equals 1 over the first resistor plus 1 over the second resistor, and so on for however many resistors there are. But this is currently not GCSE. It used to be, but weirdly they took it out. The sorts of questions that you might get on this are usually relatively simple. They'll say things like, what is the potential difference across this one, or what's the potential difference across this one, or what's the current here, for example. Almost all of the problems can be worked out with V equals IR. They test this again and again and again. So this is really, really important to make students competent with. So lots of practice on V equals IR combined with these ideas.